So let's talk about one of the most basic parts of an airplane, the propeller. I mean, it seems so simple, right? Just a spinning blade. But the journey of this one part, from just a fixed chunk of wood to a totally automatic, self-adjusting system, well, it's an incredible story. It's full of ingenuity, some really high-stakes challenges, and a tech leap that literally changed aviation forever. All right, let's get into it.
This quote just nails it. It perfectly frames the entire journey we're about to go on. We're moving from a simple one-size-fits-all tool to this incredibly sophisticated piece of machinery that gives a pilot amazing control and efficiency. It really is the difference between huffing and puffing up a hill, stuck in one gear, and just smoothly accelerating with a modern automatic transmission.
Okay, so this is where it all began. The fixed pitch propeller. The angle of the blades, we call that the pitch, is set once when it's made, and that's it. You can't change it. It's designed to do one single job really well, whether that's climbing fast or cruising efficiently. The big problem, as you can probably guess, is that flying involves a whole lot more than just one job. And that brings us right to the heart of the dilemma that drove decades of innovation, the one-speed propeller problem. Why wasn't a simple fixed prop good enough for the long haul? Well, what's really interesting is that for the absolute pioneers, like the Wright brothers, this wasn't a huge deal. Their first planes flew in a really narrow speed window. I mean, their top speed wasn't much faster than their stall speed. So for them, a single prop pitch worked just fine because the plane was always operating right in its sweet spot. But as planes got faster and more powerful, the problem became glaringly obvious. Think of the propeller blades taking bites of air. For taking off or climbing, you need a fine or low pitch. This lets the engine rev up to its max RPM and generate full power. It's just like being in first gear. But once you're cruising at high speed, that same low pitch is like pedaling your bike like a madman going downhill. The engine is screaming, but you're not getting much more speed. For an efficient cruise, you need a coarse or high pitch to take bigger bites of air. A fixed pitch prop could only ever be good at one of those things, never both. It was always a compromise. So engineers knew they had a problem to solve. But their first challenge wasn't just about figuring out how to change the pitch. It was something much more fundamental. They had to build a propeller that wouldn't just fly apart under the incredible stresses of these newer, more powerful engines. And the stakes were as high as they could possibly be. And look, this wasn't just some theoretical engineering puzzle. The very first death in a powered airplane crash was the direct result of a propeller breaking in mid-air. The technology had to get safer before it could ever get smarter. And the story of that first crash, man, it's just brutal. It's 1908, and Orville Wright is flying a demonstration for the U.S. Army. Suddenly, a piece of his laminated wooden propeller just snaps off. It hits a bracing wire, and that wire then whips around and shatters the other propeller. In an instant, the aircraft was completely uncontrollable. Orville was badly injured, and his passenger, Lieutenant Thomas Selfridge, was killed. So that crash was a huge wake-up call about the need for way stronger materials. You see this rapid evolution. We start with wood, of course, but by the 1920s and 30s, things move fast. First, we get solid aluminum blades in 1923. Then, by 1932, these incredibly strong hollow steel blades. These new materials could finally handle the power and the RPMs that were needed for the next big leap. Now that they had stronger props, engineers came up with the first real solution to the one-speed problem, the ground-adjustable propeller. The idea was pretty simple, really. You still couldn't change the pitch in the air, but a mechanic could unbolt it and reset the angle on the ground before a flight, basically tuning the plane's performance for whatever that day's mission was. And here's a perfect example of this in action, and it's a big one. Charles Lindbergh's famous flight across the Atlantic in the Spirit of St. Louis, it was basically made possible by this exact technology. He had to take off with this insane fuel load, so his team set the prop to a pretty fine pitch to get every ounce of power on that takeoff run. But it was just coarse enough to give him the fuel efficiency he needed for that long, long cruise to Paris. It was a carefully calculated compromise, and it was absolutely key to his success. Okay, so ground adjustable was a huge step up, but the holy grail was obvious, right? Everybody knew what they really needed was to give the pilot the power to change the propeller pitch while they were actually flying, and that was the next massive breakthrough. Now, the first attempts were pretty simple. They were called two-position props. A pilot could literally flip a switch in the cockpit for either a climb setting or a cruise setting. But technology was moving so quickly that these were almost instantly replaced by true variable pitch propellers. This gave the pilot a lever to select any pitch they wanted between the low and high settings, allowing for perfect fine-tuning. But here's the twist. In solving one problem, they created a brand new one. This amazing new level of control came at a price. It massively increased the pilot's workload. So now, on top of flying the plane, navigating, talking on the radio, they had to constantly fiddle with the propeller control to keep the engine happy. And in combat, this became a deadly trade-off. Seriously, put yourself in the cockpit. You're in a dogfight. Do you keep your head down, messing with the prop lever to squeeze every last bit of performance out of your engine? Or do you keep your head up on a swivel, scanning the sky for the enemy? You can't do both at the same time. The answer to that impossible question was to take the decision out of the pilot's hands entirely. The ultimate solution was the automatic, or as it's much better known, the constant speed propeller. This was the absolute pinnacle of piston engine propeller tech. So here's the magic. With a constant speed prop, the pilot just decides on the engine RPM they want. Let's say 2,700 RPM for takeoff. They move a lever to that setting, and a brilliant little device called a governor automatically and constantly changes the propeller's pitch to hold that exact RPM. It doesn't matter if the plane is climbing, diving, or cruising. The pilot just sets it and forgets it. And the impact in the real world? It was absolutely monumental. A perfect example is the Spitfire. When the Luftwaffe got their hands on captured Spits after the Battle of France, those planes had the older, manually controlled props. But in those few crucial months before the Battle of Britain, the RAF raced to fit their Spitfires with brand new constant speed units. This gave the planes a huge performance boost. And, just as important, it freed up the pilot to focus only on fighting. The Germans had no idea what they were about to face. They completely underestimated the improved plane. So this chart really sums up the whole journey, right? You can see the trade-offs perfectly. The old fixed-pitch prop is simple, it's light, it's cheap, but its performance is always a compromise. The constant speed prop, on the other hand, is complex, it's heavy, and it's expensive, but it delivers the absolute best performance in every single phase of flight. Now, I know what you're probably thinking. Okay, that's cool, but how does this automatic system actually work? So let's take a quick peek under the hood, because the genius behind it is really, really clever. The brain of the whole operation is a device called a governor. It's connected to the engine, so it spins right along with it. Inside it has these two little L-shaped weights, called flyweights. The entire system works on one of the most basic principles in physics, centrifugal force. The faster the engine spins, the more those weights want to fly outwards. And this is how it all clicks together. If the engine starts running slower than the RPM the pilot selected, that's an underspeed condition. The flyweights fall inward. This opens a valve that sends engine oil into the hub to twist the blades to a finer pitch. That reduces the load, and the engine speeds back up. If the engine is too fast, overspeed, the flyweights swing out. This opens a different valve path that sends oil to twist the blades to a coarser pitch, which increases the load and slows the engine down. And when it's perfectly on speed, the flyweights are perfectly balanced, holding the pitch exactly where it needs to be. It's just this constant, beautiful mechanical dance happening hundreds of times a minute. And what's actually doing the heavy lifting to twist those big blades? Well, during World War II, there were two main ways they did it. The famous Hamilton Standard props used the engine's own oil pressure, a hydraulic system. The other major player, Curtiss Electric, used a powerful electric motor right there in the propeller hub. You could find both types on legendary aircraft like the P-47 Thunderbolt and the P-51 Mustang. Which brings us to one last thought to leave you with. This whole evolution, from a fixed piece of wood to this automatic, self-regulating system, was an amazing technological achievement. It really makes you wonder, doesn't it? When we look back at the legendary aces of the past, how much of what we call pilot skill was really a reflection of the superior technology they just happened to have at their fingertips? It's a great reminder that in aviation, the human and the machine are always part of the exact same story.